So to answer your question, I'll try to solve a similar problem to explain the process of converting to canonical form using row reduction. So I'm starting with an example with the problem from page 49 of the textbook, as you can see here. And I'm posing the problem of converting this to canonical form for the variables 4, 5. I might have a problem, but I will try to avoid it. All right, so how do you do this? So the first thing you want to do is you want to take these the submatrix corresponding to those indices, 4 and 5, and you want to row reduce that so that that submatrix corresponding to those columns is an identity submatrix. Okay, so let me go to the second slide here. Okay, so what I said there, we want to row reduce so that these guys form an identity matrix. So we just use Gaussian reduction as usual, but where the goal is no longer to make an identity submatrix, is on the leftmost side, but specifically in these columns. And because those columns form a basis, we know that it's possible. Okay, so we do some row reduction. So for example, we'll swap the spots, those two, multiply by 1/2. And I wrote down the list of operations there if you want to try to run through it yourself. And if I didn't make any calculation errors, this should be the end result over here. So after that row reduction, I get this. Okay, so actually, what can we say right away? This submatrix is not singular, so in fact, we do have a basis. Furthermore, these are positive over here. These are non-negative, I should say. So these form... this basis gives you a basic solution that's feasible, and I could write it out explicitly over here if I wanted to. So just, oops, it's not working. To clarify over here, the basic solution would look like, well, let's see. So it's basic, so we want all of the coordinates outside of our basis to give a value 0. And within our basis, we should just read off what these give. So the first coordinate would have to be a 1. By first, I mean the fourth coordinate. And the fifth coordinate would also be a 1, corresponding to the 2 ones over here in order. And this would be our basic solution. We can see it's feasible because the entries are non-negative. All right. So then the last step then is to convert this to canonical form then is to update the objective function. So originally our objective function looks like this over here, the first line. And what we want to do then is we want to modify it using the constraints we have over here. We want to modify it so that C4 and C5 are 0, and that'll satisfy the definition of being in canonical form. So what do? Well, we want to clear out this 2 over here. So how do we clear out the 2 over there? Well, we look at the identity where this first row dot x is equal to 1. So this term over here is 0 for any feasible solution. Since it's 0 for any feasible solution, I can update the objective function by adding a multiple of that, and it doesn't change the value of the objective function at any feasible solution. So really, we haven't changed the problem very much. Or we haven't really changed that at all as far as we're concerned. Okay, so I subtract 2 times this with the goal of having this coefficient over here, having 2 subtracted from that so that it'll become a 0. And similarly, I want to get rid of this 1 over here, so I subtract 1 times this equation over here to get rid of that. So that's where the 2 and the 1 come from. And when I do that, I do all of the calculations, and I end up over here with the updated objective function, where there's zeros where I wanted. And I'm in canonical form now. So this is the new updated objective function. This is the new constraint. And of course, you also need to ensure that x is greater than or equal to 0. So I didn't write it out in full, but I hope this helps. Any further questions you could ask on Piazza?